Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to talk on the module Diffusion of Impurities VLSI from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the classification of ICs. Next, the detailed process of IC fabrication will be discussed. Thirdly, we will discuss about the impurity of doping, that is impurity doping. Next, we discussed about the nature of diffusion. Next, the dynamics of diffusion process will be discussed in this module. So students, let us start with a basic introduction about the module. The concept of IC was first introduced in the year 1958. So due to its small dimension, low cost and very high reliability, ICs have widely been used in the various components like mobiles, computers, laptops, and many more devices in the digital world. So an integrated circuit IC can also be called as a microchip, and it is basically a collection of small discrete circuits or a small chip that is made up of a semiconductor material like silicon. All ICs consist of both active and passive components, and the connection between them are very small. All the components, active and passive, they are interconnected through a fabrication process. So they are mostly available at dual inline packages, metal cans, and also ceramic flat packs. So they may be 8 pin, 10 pin or 14 pin depending on the specification of the manufacturer. Advantages and disadvantages of integrated circuits ICs. So let us first discuss about the advantages. It is miniaturized in size. For the production of hundreds of ICs, the cost of production will be very low and less time consuming. The small size of ICs causes lesser power consumption and lesser power loss. Let us now discuss the disadvantages. Some complicated ICs may be costly. The power rating for most of the ICs does not exceed more than 10 watts. Thus, it is not possible to manufacture high-power ICs. Some components like transformers and inductors cannot be integrated into an IC. They have to be connected externally to the semiconductor pins. Increased operating speed because of the absence of parasitic capacitance effect. As the ICs are produced in bulk, the temperature coefficients and other parameters will be closely matching. All the ICs are tested for operating ranges in a very low and a very high temperatures. It is difficult to achieve low temperature coefficient. It is difficult to fabricate an IC with low noise. And lastly, there is a large value of saturation resistance of the transistors. Let us now study the classification of integrated circuits. All the ICs have interconnected discrete device inside the chip and the corresponding external connecting the terminals outside. So each pin may have each function and may vary according to the manufacturer's design. So in order to make the circuit fully operative, the pins in the IC must be used for supply voltage, input and output connections, and also some external components according to the need of the manufacturer. ICs can also be classified on the basis of their chip size as given below. That is, first, the small scale integration SSI 3 to 30 gates per chip, medium scale integration MSI 30 to 300 gates per chip, large scale integration LSI 300 to 3000 gates per chip, very large scale integration VLSI more than 3000 gates per chip. Let us now discuss about the other classification of ICs based on their application. So they are classified as linear integrated circuits and digital integrated circuits. So linear ICs are used in cases when the relationship between the input and the output of a circuit is linear. An important application of linear IC is the operational amplifier, commonly referred as op-amp. Now, digital IC, when the circuit is either in on state or off state and not in between the two, the circuit is called as a digital circuit. ICs used in such circuits are called as digital ICs. They find wide applications in computers and logic circuits. Now, ICs can also be classified on the basis of the process of fabrication as monolithic ICs, thick and thin film ICs, hybrid or multi-chip ICs. Let us now first discuss about the monolithic integrated circuits. Monolithic ICs refers to a single stone or a single crystal. The single crystal refers to a single chip of silicon as the semiconductor material on top of which are all the active and passive components needed are interconnected. This is the best mode of manufacturing the ICs as they can be made identical and produces high reliability. The cost factor is also low and can be manufactured in bulk in a very less time. They have been found applicable for the ICs used for AM receivers, TV circuits, computer circuits, voltage regulators, amplifiers, and so on. So a schematic of the monolithic IC in can type enclosure is shown over here. Thin and thick film integrated circuit. Let us first discuss about the thin film ICs. This IC is fabricated by depositing the films of conducting material on the surface of a glass or a ceramic base. So here the resistors are fabricated by controlling the width and the thickness of the films and by using different materials selected for their resistivity. So for the capacitors, a film of insulating oxide is sandwiched between the two conducting films. So a spiral form of the film is deposited onto the IC to create an inductor. So students, mainly two methods are used for producing thin films. Number one, vacuum evaporation is used, in which vaporized material is deposited on a substrate contained in a vacuum. Secondly, cathode sputtering, in which the atoms from the cathode made up of the desired film material are deposited on a substrate located between a cathode and an anode. Now, thick film ICs, they are also commonly called as printed thin film circuits. The desired circuit pattern is obtained on a ceramic substance by using a manufacturing process called as silk screen printing technique. So here the inks used for printing are usually the materials that have resistive, conductive or dielectric properties. They are selected accordingly by the manufacturer. The screens are actually made up of fine stainless wire mesh. The films were fused to the substrate after printing by placing them in the hot high temperature furnaces. Fabrication techniques used for thin film passive components, they are adopted for thick films as well. As with thin film circuits, active components are added as separate devices. Hybrid or multi-chip integrated circuits. It is fabricated by interconnecting a number of individual chips. The active components are diffused transistors or diodes. The passive components may be a group of diffused resistors or capacitors on a single chip, or they may be thin film components. Interconnection between the individual chips is made by wiring process or a metallized pattern. Hybrid ICs are also known to provide a better performance than the monolithic ICs. Although the process is too expensive for mass production, multi-chip techniques are quite economical for small quantity production and are more often used as prototypes for monolithic ICs. Process flow for the fabrication of IC. The fabrication of ICs consists basically of these following process steps. First, starting material to polished wafer or crystal orientation, crystal orientation and planes. Second, impurity doping, which may be done by diffusion and ion implantation. Third, passivation layer, that is the oxidation. Next, the deposition of metal contacts, that is metallization. Lastly, or we have the lithography and then etching. The process flow from the starting material to a polished wafer. So this is the first process in the fabrication of IC. So first we take the starting material, which can be SiO2, that is distillation and reduction, and then this starting material is grown into the crystal, single crystal, and then by grinding and saw polish it is made to a wafer. So starting materials, silicon dioxide for a silicon wafer and gallium and arsenic for gallium arsenide wafer, they are chemically processed to form a high purity polycrystalline semiconductor from which single crystals are grown. So the single crystal ingots are shaped to define the diameter of the material and sawed into the wafers. These wafers are etched and polished to provide smooth, specular surfaces on which the devices will be made. So, there are two methods in order to fabricate a silicon crystal. First is the Czochralski method, and second one is a float zone process. So here we will first discuss about the Czochralski method. This technique uses an apparatus called as crystal puller as shown in this figure. So the puller has three main components: a furnace which includes a fused silicon dioxide crucible, a graphite suspector, a rotation mechanism which is clockwise, a heating element and a power supply. Second is a crystal pulling mechanism which includes a seed holder and rotation mechanism counterclockwise, an ambient control which includes a gas source such as argon, a flow control and exhaust system. The puller has an overall microprocessor based control system to control the process parameters such as temperature, crystal diameter, pull rate, and rotation speeds. In crystal growing process, polycrystalline silicon (EGS) is placed in the crucible and the furnace is heated above the melting temperature of silicon. So a suitably oriented seed crystal 111 is suspended over the crucible in seed holder. The seed is inserted into the melt, part of it melts, but the tip of the remaining seed crystal will touches the liquid surface. It is then slowly withdrawn. Progressive freezing at the solid liquid interface yields a large crystal. A typical pull rate in few millimeters per minute, but for large diameters, silicon ingots an external field is applied to the basic Czochralski puller. The purpose of external magnetic field is to control the concentration of defects, impurities, and oxygen contents. So the second type of process is a silicon float zone process whose schematic is shown over here. The float zone process can be used to grow the silicon that has lower contamination than that normally obtained from the Czochralski technique. A high purity polycrystalline rod with seed crystal at the bottom is held in a vertical position and rotated. So the rod is enclosed in the quartz envelope within which an inert atmosphere is maintained. So during the operation, a small zone of the crystal is kept molten by a radio frequency heater, which is moved from the seed upward so that this floating zone traverses the length of the rod. The molten silicon is retained by surface tension between the melting and the growing silicon faces. As the float zone moves upwards, a single crystal silicon freezes at the zone's retreating and grows as an extension of the seed crystal. So students, materials with high resistivities can be obtained from the float zone process than from the Czochralski process because it can be used to purify the crystal more easily. So let us now discuss about the impurity doping. Impurity doping is the introduction of controlled amounts of impurity dopants into the semiconductors. The practical use of impurity doping has been mainly to change the electrical properties of the semiconductors. So there are two methods of impurity doping. First is diffusion and second is implantation. Let us first discuss about the diffusion, which is done at elevated temperatures. Dopant atoms are placed on or near the surface of the wafer by deposition from the gas phase of the dopant or by using doped oxide gas sources. Doping concentration decreases monotonically from the surface and the profile of the dopant distribution is determined mainly by the temperature and diffusion time. So this has been explained in this figure. Ion implantation. The dopant ions are implanted into the semiconductor by means of an ion beam. Doping concentration has a peak distribution inside the semiconductor and the profile of the dopant distribution is determined mainly by the ion mass and the implanted ion energy. Let us now discuss about the nature of diffusion. Diffusion describes the process by which atoms moves in a crystal lattice. Although this includes self-diffusion phenomena, so our goal is to study the diffusion of impurity atoms that are introduced into the lattice for the purpose of altering its electronic properties. So let us first discuss about the interstitial diffusion. It occurs when the impurity atoms moves through the crystal lattice by jumping from one interstitial site to the next. Interstitial diffusion requires that jump motion occur from one interstitial site to another adjacent interstitial site. This process is relatively fast because of the large number of vacant sites of this type in a semiconductor. Impurities such as sodium and lithium moves in the silicon by this mechanism, and it is schematically shown in this figure. Next one is substitutional diffusion. So here an impurity atom wanders through the crystal by jumping from one lattice site to the next, thus substituting for the original host atom. However, it is necessary that this adjacent site be vacant, that is, vacancies must be present to allow the substitutional diffusion to occur. Next is interstitial substitutional diffusion. In this case, impurity atoms occupy substitutional as well as interstitial sites. However, they only move at a significant rate when in interstitial sites. So, the dissociative mechanism by which a substitutional impurity atom can become an interstitial, leaving behind a vacancy, can be the controlling factor for this process. Copper and nickel moves in silicon by this mechanism, as do zinc, cadmium and copper in gallium arsenide, and this type of process is shown over here. So an alternative pathway for interstitial diffusion is the kick-out mechanism. Here a rapidly moving interstitial diffuser can move into a substitutional site by displacing an atom which is already in place, resulting in the formation of a self-interstitial. Let us now discuss about the another type of diffusion, that is interstitial diffusion. This is a modified version of substitutional diffusion. Here interstitial atoms can be annihilated by polishing substitutionally located impurity atoms into interstitial sites. These impurities can now diffuse to adjacent substitutional sites and create new self-interstitials. Thus, the interstitial position of the diffusing impurity atom is purely a transition state in moving from one substitutional site to the other. This increases the concentration of vacant substitutional sites over its equilibrium value, so that interstitially diffusion is somewhat faster than substitutional diffusion. All substitutional diffusers move in part by this mechanism. So the diffusion of boron and phosphorus in silicon is dominated by this process. Interchange diffusion. This occurs when two or more atoms they diffuse by an interchange process. Such a process is known as a direct interchange process when it involves an impurity and the host atom, and as a cooperative interchange when larger number of host atom is involved. Second type of diffusion is a grain boundary diffusion. Diffusion also occurs by movement along dislocations and grain boundaries. This process is anisotropic, being much faster in directions parallel to the dislocations, core or to the grain boundary edge than at right angles to it. Furthermore, atom movement is two or more orders of magnitude faster than that obtained by the lattice diffusion processes outlined above. Now here enhanced diffusion along dislocation often leads to emitter-collector shorts in bipolar devices by the formation of diffusion pipes. Next type is combination effects. Combination of these mechanisms may occur within a crystal. For example, a certain fraction of impurity atoms, they may diffuse substitutionally and the rest interstitially, resulting in two-stream process. So with many substitutional diffusers, it is necessary to assume that diffusion proceeds in part by a substitutional mechanism and partly by interstillacy mechanism. Finally, must be emphasized that diffusion describes the movement of impurities and not their ultimate destination. Thus, it is possible that some of the diffusing species may end in substitutional sites, with others in interstitial sites. Let us now study about the dynamics of diffusion process. In diffusion, the dopant material migrates from the region of higher concentration to the regions of lower concentration in a wafer, which is called as mass diffusion. So the process is governed by Fick's law of diffusion, which states that the mass flux of the dopant is proportional to the concentration gradient of the dopant material in the wafer and a material constant characterizing the movement of the dopant material in the wafer material. So Fick's law of diffusion is given by J equal to minus D del C by del X, where J is the mass flux, D is the diffusion constant of the dopant in the wafer material, C is the concentration of the dopant in the wafer material, and X is the coordinate direction of interest. Here the negative sign indicates that the flow of the dopant material is in the direction of decreasing concentration. So the diffusion constant D is temperature dependent constant that characterizes the diffusion of one material to the other. For general purposes, the constant is well calculated by D equal to D naught e to the power minus EA by kBT, where D naught is the frequency factor, a parameter related to the vibrations of atoms in the lattice. Kb is the Boltzmann constant and EA is the activation energy, which is the minimum energy a diffusing atom must overcome in order to migrate. So in a doping by diffusion, the dopant is first delivered to the surface of the wafer, after which it diffuses into the wafer. The resulting distribution of dopant within the wafer is therefore a function of both the time and the depth from the wafer surface. So in order to determine this distribution, one solves an equation representing the idea that mass is conserved as the dopant diffuses within the wafer. So the version of the conservation of mass that applies at a point within a substance is called as the continuity equation. So as this partial differential equation is first order in time and second order in depth, we require one initial condition and both boundary conditions in order to solve it. Initial condition is that the concentration of dopant at any depth is 0 at t equal to 0. That is Cxt equal to 0, which is equal to 0. So another boundary condition is that the surface concentration goes to some constant value for t greater than 0 and remains at that constant value for all the times after that. The second boundary condition comes from the wafer thickness being significantly larger than the depths to which the dopant diffuses. So in equation form, these two boundary conditions are respectively Cx equal to 0, t greater than 0 is equal to Cs, Cx tending to infinity, t greater than 0 equal to 0. So the solution to equation 1 incorporating these boundary conditions is Cxt equal to Cs ERF C as a function of x by 2 root of dt, where CS is the surface concentration and ERFC as a function of lambda is the complementary error function, which is given by ERFC lambda equal to 2 by root of pi integral x to infinity e to the power minus lambda square d lambda, where lambda is a variable. So the variation of C by CS with x is shown in this figure for various values of t, and the diffusion length gives a rough estimate of how far the dopant has diffused into the substrate material at a given time. As the concentration profiles are asymptotic, no single length gives us a true cutoff, at which point the dopant concentration is actually zero. So the characteristic length is called as the diffusion length, which is given by x diff approximately equal to root of 4 dt. Let us now discuss about the ion implantation. Ion beam implantation is a process that changes the physical and electronic properties of a material by forcibly embedding different types of ions into the material. So the use of ion implantation was to modify the electrical properties of semiconductors, metals, insulators, and ceramics. The technique is best suited to the materials like semiconductors, where small numbers of implanted particles can cause major changes in the material's electrical or physical properties. Implantation energies, they are between 1 keV and 1 MeV, resulting in ion distribution with average depths ranging from 10 nm and 10 micrometer. So ion doses vary from 10 to the power 12 ions per centimeter square for threshold voltage adjacent to 10 to the power 13 ions per centimeter square for the formation of buried insulating layer. So the dose is expressed as the number of ions implanted into 1 centimeter square of the semiconductor surface area. The main advantage of this ion implantation is that its more precise control and reproducibility of impurity doping and its lower processing temperature compared with those of diffusion process. So students, let us now summarize what we have learnt in this module. First, we discuss the classification of ICs and the various classifications of ICs depending upon different parameters. Secondly, a detailed process of IC fabrication was discussed in this module. Third, the impurity doping process was also discussed. Next, we discuss about a very important process of impurity doping, that is diffusion and its nature. Next, we discussed about the dynamics of diffusion process in this module along with another important impurity doping process, that is ion implantation. Thank you.